Thank you. Good morning. My name is Victor Martinez Pacheco. I am an architect from the Higher Technical School of the Architecture and Building at the Polytechnic University of Cartagena, Spain. I'm going to present the project 3D printed humanitarian aid settlements for emergencies response, carried out jointly with Dr. Maria Mestre Martin. The project is the result of more than 2 years of continuous work and consists of an investigation of architecture in catastrophes, characterization of the structural behavior of 3D printed piers, and development of a constructive system and its application in the design of a refugee camp and a school in the Central African Republic. The project consisted in 3 main parts. Firstly, catastrophes and the role of emergency architecture in this situation. A second chapter of 3D printing research, prototyping version laboratory with the aim of developing a constructive system that offer solution to the problems that the previous states posed. And finally, an example of application of this system in a school or a refugee camp in the Central Africa. Well, but why emergency architecture? If I had to define the architecture at this point, I will say that it's a method of solving problems, and disaster are a good starting point to look for problems to solve. Statistically, all countries suffer catastrophes equally. However, whether a catastrophe turns into humanitarian crisis depends on the vulnerability factor. These are some diagrams of humanitarian catastrophes in recent years and their incidence in deaths by event and country. And this is a comparative DALI's chart between Spain and the Central African Republic. The yellow color represents non-infectious diseases associated with developed countries, and the dark color represents infectious disease. In turn, the people most affected by this are the most vulnerable groups. What in this context are women and children. Obviously, this chart was before coronavirus. So, how can we help a population in a context of humanitarian crisis? Here is what we call the 8 phases. First, survival, prevent people from dying. Contingency, keep the previous measures during the course of the anomaly. And resilient, what is restoring a normality that also prevents the crisis from happening again. Our project seeks to focus on this point, the recovery of normality and the empowerment of population. But of course, dealing with a situation like this in practice involves a lot of problems. Problems such as transportation, weight, blow roads, or priority of resources to supply primary needs. On the other hand, the water. The water is very important in emergency architecture. In emergencies, there is no water. There is no drinking water, and there is no water to build. So water factor is very important. So it was decided to experiment to achieve a constructive system for emergencies that met a series of requirements. It was essential that the system were light and did not require water. In addition, after analyzing the architecture of emergencies today, the state of the art, it was established that it was very important to start designing from an environmental impact perspective. And after some tests, we understood that we had to change the technology and the technique. 3D printing is the only manufacturing system that allows the production of parts whose filling is neither solid nor hollow. We can customize the interior, its density, but we can also customize the internal geometry with which we are going to fill the part. Sure, 3D printing in buildings already exists, but in concrete and large format, we needed a system that allowed us to open source printer and very low cost print. That is, with small piece achieve large structures. And this is how the prototyping of version began. 27 geometric versions were made until reaching one that has several stages of assembly, revision, investment, node generation, optimization, tolerances, joints. Finally, get a system that worked, but geometrically only. Why I said geometrically? Because there was a problem. In reality, 3D print is just a succession of two-dimensional layers whose volumetric behavior depends on the adhesion of the between the layers. So, an experiment was conducted using more than 4,000 3D printed elements, and it was tested in the National Reference Chemical Center laboratory. They were coded, they were tested, were analyzed, and finally, a recycling phase of plastic bottle was carried out. They were selected, were crushed. I have some crushed water bottle crushed. Was transformed into pellet and in filament, in 3D printed filament, to manufacture our structure made with 3D printing recycled bottles. All of that in order to determine the influence of fill density, orientation, and internal pattern on the resistance of 3D. This laboratory research started in July 2018 and ended in September 2019. 18 months in which tensile, flexural, Sharpie impact, deflection under thermal load, Rockwell microscopic analysis, crushing, injection, and brick test was carried out. And the trial sought to determine the influence of current main internal filling patterns, grid, line, triangular, hexagonal, and cubic, the influence of printing density, 20%, 30%, 40, 60, 80, and 100% in fill, and its orientation, the printing orientation, the three main axes, in its structural behavior. Once we obtain the results, we carry out a statistical study, and well, this graph shows the deformation stress diagram of some of the specimen state, where we reached the conclusion that we could obtain with density of 20% resistances higher than 80%, with the important implication in weight, material consumption, and time, and of course, environmental impact. This result was a success. It means that with a fifth of the material, we achieve 80% of the resistance. This makes it a very light system with low material consumption. We made simulation of the matrix entering three-dimensional modules. We decided at this point, and in light of the previous analysis, to locate ourselves in the Central African Republic. We had to choose a location, so we choose Central African Republic. So the structural simulation had to consider the loss due to the monsoon rains, and this led us to the optimal model of behavior was 5 by 5 meters. But of course, the previous was a simulation, and we went to make real buildings. So we made a prototype to real scale in a biodegradable material in case it did not work, where we could test the pros and cons of the system in real life. The prototype was assembled for a week with wind, rain, and a lot of sun. It resisted, and we took it apart. As you can see in the time lapse, the assembly of the real scale prototype of 10 square meter looked less than a day for a single person. This images was recorded last summer. And the most important is, it worked, but other important thing is the whole prototype fit in those two boxes. Easy of transportation is one of the main initial requirements. So once we verified that the system was working, we went on to propose an example of a project application. We said that humanitarian catastrophes have a higher impact on the most vulnerable groups, and that in this context, they are women and children. The fact of building a school has a brutal impact on the future of population. Today, we have situations like Syrian war that has lasted almost 9 years. There are children who have been 9 years without education. An example of this situation is the Central African Republic, specifically Bria, where one of the largest refugee camps in the world is concentrated. Improvised and planned camps for displaced people, resulting in chaotic, semi-permanent cities. It is decided to update the existing field according to the recommendation of the United Nations. And if I had to name a urban criteria in such planning, it will be vulnerability again. When designing a field, it's essential to project for women, project for children, project for elderly, sick people, because they are extremely vulnerable groups in this context. And the measurements go from the orientation of the public toilets, distance of the source of position of the houses, and specifically the situation of a school. A school that has services not only for children or for teaching, but it is conceived as a social goal, contemplating the possibility of being used in the afternoon even by parents. In such a context, a school is building resilience. And we said that there was an optimal 5 to 5 meters module, which is enough to fulfill all the school services. The project use program is organized in technical band that serves of the rest of the school, services, library, facilities, first aid, and some classroom, N, L, and XL sites. And of course, when designing such an architectural and sustainable project, starting from the fact that it doesn't require industrial machinery at all. So we started with the design of an air conditioning system by solar chimneys. It works balancing the temperature by differential pressure in the fluid. The cover forms is a consequence of these chimneys. And on the other hand, sorry, it gave it in Spanish. On the other hand, the water collection is produced in two different manners. By collecting rainwater that goes to the settling system, filter, purification, and deposit, and at ground level, water goes directly together with the rest of sanitation to a tiger toilets system that is redirected to phytodepilation space. Wastewater is conducted to a phytopurification and irrigation tanks for the cultivation fields of hemp. This is a view of the school, and that we are proposing is a self-sufficient building in electricity, water, sanitation, air conditioning. So in no case it stops to be useful to the population for which it has been designed. So this is an example of a sustainable school made with 3D printing architecture that aims to protect the environment and also offers a new conception of architecture completely made with a domestic 3D printer for short periods of time human settlements. Recycling and circular economy are definitely the future of the building, and we must include in these strategies the design for people and for the planet. So thank you very much for your attention.
Thanks, Victor, for your sharing. Yeah, appreciate you taking time off. Yeah. So, any questions for Victor from the floor? Okay, if not, Victor, I do have a few questions for you. Yeah. So, just how long did you take to conduct your research?
Well, the research was conducted by 1 year, the laboratory research, and all the research was made in 2 years with the state of the art, the previous investigation in architecture, emergency architecture, the laboratory, the 1 year of laboratory analysis, and the printing of the piece. It was a lot of piece to make a building. I have some samples. The piece made with 3D printing, and of course make the school project that was an example of the application of this constructed system. 2 years.
Okay, thanks for your sharing. Yeah, so any questions for Victor? If not, let me ask you another question, Victor. So in terms of general application, is there any real-time application of your research at the moment?
I'm sorry, can you repeat?
Is there any general application of your research or your 3D printing project at the moment?
I lost the communication. If is any application out of the
lab?
My connection is failing.
Okay, one moment. Let me send you the.
Is any application of my okay?
Yeah.
Outside my research. Well, it was only theoretical research. We started to talk with non-governmental organization like Oxfam. Oxfam has been very useful. They have a lot of information, and they help a lot with all the process of the research. And we are collaborating in the study to implement some tests in Central African Republic, but not by the moment. By the moment, it's only in research state.
Okay, thanks. So, do you see any commercial viability with regards to your research?
Sorry, I heard very bad.
Yeah, no problem.
Commercial viability. No. Actually, the idea of use open source printers is very important because the use of open source software, open source hardware, and open source architecture is important because we are talking about humanitarian system, not only for the humanitarian. It's because making a solution for everyone is very important, and commercialization, like talking with an enterprise or other thing, is not in the line of work. We want to make it. We are very happy of the interest of many organization or enterprise, but we are not looking for bring to commercial application. We are going to bring the real application.
Oh, okay. Thanks for your answer. So one last question from me. So I will type in the chat box. Yeah. So
thank you.
So what are some of the potential rejections you are expecting, especially when you are dealing with schools, right?
Well, that's easy. It hasn't been done. It's plastic, is 3D printed, and is a very unusual situation. So it's a good cocktail to find um, rejection. No? In when we start with a new technology as 3D printing, it's very hard to find a real application. And but it's a new technique, and we must investigate it. We are looking for make more experiments, more applications, more um, more tests. No, but it's important to remark that is for emergency situation. So we must make it real, but we must stand that is for emergencies situation. So there is a lot of people that don't have any solution in that situation, and we must be open-minded to solve that situation.
Yeah. Okay. Thanks for your answer and your presentation earlier. Yeah. I hope that you have enjoyed your session. Yeah. So the session is actually recorded. Just for your information, we have a presenter in the morning. Professor Carlos is the keynote. He's shared a little bit on details on 3D printing and all. So we will be sending you the link of morning session as well. So hopefully it will help you to advance your research in a positive manner. Yeah. So appreciate your sharing. So thanks. Look forward to your future participation, and good luck for your PhD journey. Yeah. Okay.
Thank you. Thank you very much.